Good morning, dear students. My name is Ferhan Mazher, and today is 14th of October 2021. And right now, I am with the 11th Cambridge class. And the subject we are studying is Physics 5054. It's Cambridge O Levels Physics. Today, we have set our hearts to solve May-June 2021 2-1 paper. This is paper 2. We call it theory paper. And in this session, we will solve the section B of this paper. Section A of this paper we have already solved, and that has been uploaded in my YouTube channel. So if you go to the playlist and if you go to my channel from the playlist of where we have the name of the playlist is the preparation for the Physics 5054. There you will find this playlist where we have zone 2 papers, and you can find that paper. So let's start today's paper. And we are going to attempt the B paper, the section B of this paper. Section B is starting from question number 8, and here we go. Okay. So figure 8.1 shows a stationary horse and its rider about to jump over two fences. This is the horse which is about to jump, and these are the two fences. Over these fences, it will jump. He says figure 8.2 shows a side view of the horse. On the figure 8.2, draw and label the forces acting on the horse. Include the force that the rider exerts on the horse. Label this force F. Okay. So let me show you my solution. We have to draw forces. So this is the paper we are going to attempt. And let's go to the question number 8. We will go to question number 8. Okay, so here we come. So the question was, it's a 3-mark question, that label the forces which are acting on the horse. So the one force is the weight of the horse, which is approximately here will be the center of gravity of the horse. So the weight of the horse is acting here, and I have represented it with this vector, and you can label it as weight. So the weight of the horse will be acting here. The rider's weight is acting here on the saddle, on the horse. Here, with the horse will be pushing the earth downward, and the earth will be reacting here. So the force of reaction from the earth is here. Okay. So these are the forces which are acting on the horse, and this is how you will show them. It's a 3-mark question. Okay, so let's go to the next question. Then he says, explain how the Newton's third law applies to the force F. It's a 2-mark question. Okay, so this is the force F which the rider applied on the horse. Okay, so when the rider will apply force F on the horse will apply a force on the rider, and both these forces will be equal in magnitude but opposite in direction. The rider applied the force on the horse will apply the force on the rider. Both these forces will be equal in magnitude but opposite in direction, and they will act on different bodies. One force will be acting on the horse, the other force will be acting on the rider, and equal in magnitude but opposite in direction. So let me show you my answer. Rider applies force on the horse apply force on the rider. Both forces are opposite in direction and equal in magnitude. So it's a 2-mark question. Hopefully you have understood. So let's move to the next question. The next question coming up on your screen is, here we go. Figure 8.3. Figure 8.3 shows a side view of the two fences. They both have the same height and a uniform density. on each fence in the figure 8.3, mark with a cross the center of mass. It's a 2-mark question. You see, this body has uniform thickness, so its center of mass will be exactly in the middle of its height. So just check what's the height, and exactly in the middle put a cross. This fence here, its lower portion is wider and its upper portion is less wide. So its center of mass will be lowered as compared to the center of mass, this body. Okay, so you put a cross here somewhere lower than the cross you put here. It's a 2-mark question. Let me show you my answer. So there we go. Sorry. So here you can see that we have put a cross here exactly in the center of the height, in the middle of the height. And the center of the mass for this body will be little lower than this one. Okay. Hopefully you understand how we have done this. So let's go to the next part. Next part is explain why a wider base makes the fence more stable. You see, when the base is wider, the body becomes more stable. Why the body becomes more stable? Because you see, if the base is wider, the line of action of the weight always remains inside the base. If the base is wider, the line of action of the weight of that body most of the time will remain inside. When you disturb it, the base, the line of action of the weight will remain inside the base. So the body will not topple. For example, if you disturb it, you apply the force on this fence towards right side. So when the fence will go right side, the line of action will be inside the base and it will be to the left side of the center of, sorry, the point of support, and it will bring the body back. For example, if you disturbed it, you applied a force on towards the left side, so the body will tilt to the left side, but the line of action of the weight will be on the right side, and it will not go out of the base, and it will bring the body back to the left, to the right side, so the body will not fall. Okay. The words we used is when base is wider, line of action of the weight remains inside the base. So a larger force will be required to topple the fence. So if you, the small amount of force is applied, the body will tilt a little bit, but it will not totally topple. It will come back. So it makes the body more stable. So that was the, okay, so let's move to the next part. So we are done with these 2 parts. The next question coming up on the screen. The total mass of the horse and rider is 520 kg. As they approach a fence, the horse and rider have a total kinetic energy of 4,000 joules. Calculate their speed. So if we know the kinetic energy and we know the mass, we can find the speed. You know, the kinetic energy is equals to 1/2 mv square. So in kinetic energy is equals to mv square. We know the kinetic energy, we know the mass, so the V can be found. It's a 3 marks numerical. Let me show you my work. And let's see what we can do. So it's a 3 mark numerical. Here we go. So on your screen, this, I have written there that the kinetic energy is equals to 1/2 mv square. So if you make the V square alone, it will be this 2 go to the other side, multiply with the kinetic energy, 2 multiply kinetic energy divided by m. Just put the values there. V square will be equal to 2 multiply 4,000 divided by 520. So when you enter these values in your calculator, V square will be equal to 15.385. So take square root on both the sides. So V will be equals to a square root of the 15.385, and that is 3.9. So the velocity will be, or the speed will be 3.9 meter per second. It's a 3-mark numerical and it's very easy. I hope you understand. But here you should remember the demand of the question is that you should remember the formula of the kinetic energy. Kinetic energy is equals to 1/2 mv square. Hopefully you have understood this. So let's move to the next part. Okay. This one is little tricky. The center of mass of the horse and the rider is 1.4 meter above the ground. The maximum potential energy gained by the horse and rider as they jump over the fence is 3000 joules. Calculate the maximum height above the ground of the center of mass during the jump. The gravitational field strength G is 10 Newton per kg. Okay, now, now we know that the potential energy gained during a jump is 3000 joules, and the rider is already at a height of 1.4 meter from the ground. So the potential energy gained is 3000 joules. You know the formula for the potential energy is mgh. So we know the potential energy, we know the mass, that's 520 kg. We know the G value, that is 10 newtons per kg. We can calculate how much height will be gained. And then I can calculate what is the total height. The rider is already 1.4 meter above the ground. Okay. So let's start. Let's do the numerical. I can show you my work. Okay. So here you can see that the potential energy is equal to mgh, and here the question demands because they have not given the formula of the potential energy in the question. So you should remember this formula. Okay, potential energy is equal to mg. The value of the gravitational potential energy is 3000. The mass is 520. The G value is 10. The H we want to find out. So I will make H the subject of the formula. So this 520 and 10 will go on the other side. Here they are multiplying. So on the other side, they will divide. 520 multiplied 10, that's 5200. When it goes to the other side, it will divide. So the height will be 3000 divided by 5200. And that will be 0.576, which is approximately, when you round it off to one significant figure, so that will be 0.6 meter. So the total height, the rider was already at a height of 1.4, and it will gain this much height, 0.6. So the total height will be 2 2 meter plus the 1.4 plus 0.6, that will be 2 meter. So the height will be 2 meter. So this is question number 8C, its second part. It's a 3 marks numerical. I hope you have understood. This last portion is a very tricky thing to understand it from the statement of the question, that what he's basically asking. Okay, so now the question number 8, its marking scheme is showing up on your screen. What you can do, you can pause the video and have a look at this marking scheme. I have already checked it. And okay, so here we go. So you can see our answers are perfect. You can pause the video and take your time to look at this. Okay. So let's go to the next question. The next question is question number 9. So figure 9.1 is the current voltage graph for a filament lamp. So one very important thing about this graph is that here it's about a filament lamp. On the y-axis, we have current. On the x-axis, we have voltage. So this graph is basically a curve. And you know that the slope of this graph will be I by V, and that is the reciprocal of the resistance, I by V. That's the reciprocal of the resistance. So the slope here is basically, slope is equals to 1 by R. So basically, for example, if the slope here is gradually decreasing, the slope here has gradually decreased. So it means the resistance has gradually increased. Slope of this graph is equals to 1 by R, because the I is on the y-axis and V is on the x-axis. Okay, so let's go to the question. What is the question? Figure 9.2 shows the incomplete circuit diagram of the circuit that a student uses to obtain the readings for the graph. So here we have a battery, we have a switch, we have ammeter. Complete the circuit diagram using suitable circuit symbols for the lamp, a voltmeter, and a variable resistor. So we will complete here. We will put here a variable resistor, then we put a fixed resistor here. And across the fixed resistor, I will put a voltmeter parallel to the fixed resistor. So it's a 3-mark question. Let me show you my answer. Question number 9, and its first part. Okay. So here you can see that we have drawn it. We have put a lamp here. Okay, so we are supposed to put a lamp here. We put a lamp here. We have put a variable resistor here. And across the lamp, I have put a voltmeter. It's a 3-mark question, very easy question. Okay, now he says the ammeter used by the student has a range from 0 to 10 ampere, from 0 to 1 ampere, from 0 to 100 milliampere, and from 0 to 10 milliampere. Describe how the student uses the different ranges to obtain readings, which allow all 9 points to be plotted precisely on the graph while using the ammeter safely. Okay, so here, look at this. In the start, the minimum amount of current is 0, and that when you started the experiment, the amount of current is here is like something like 0.2 something, and here 0.5, here 0.65 something. Here you have 0.8, and then here you can see 1 point something. Here you have 1.2, 1.2 something ampere current. Here the current is like 1.4 something, here 1.6 something, and here the maximum current is 1.8 ampere. So 1.8 ampere is the maximum current which flows through the filament lamp. And the minimum current flowing is, which we recorded, is 0.2324 ampere. So remember these numbers, okay? So maximum current flowing is 1.8 ampere. So look at the ranges he gave you. Okay. So when the current is, you cannot use these. These cannot be used. Okay. These two cannot be used. We can only use these two. These two can be only used. Okay. Remember this thing. The reason is the maximum current which flowed is 1.8, 1. You see, if I show you there, for example, 1.8 ampere, that cannot be measured with anything. You cannot measure 1.8 with these three. Okay. So when the current is more than 1 ampere, then you have to set your ammeter at 0 to 10 ampere reading. And when the current is below 1 ampere, then you have to use like 0.234 ampere. You cannot use these one. You have to use this one, the second one, 0 to 1 ampere. So for the current, when the current is more than 1 ampere, I will use this setting, which is 0 to 10 ampere range. And the current, which when the current is less than 1 ampere, I will use this range of the ammeter. These two will not be used. And the why we use these ranges, because so that the ammeter shows a visible, a significant, a large deflection for that amount of current. And one very important thing, when you start your experiment, you will use the maximum range. So because we are not sure when we start the experiment, we are not sure that how much current will flow through the circuit. So when you start your experiment, then you use the maximum range, and then you gradually you check that how much is the pointer moving. If the pointer shows a very small reading, then you can lower the range. If it's showing a significant reading, for example, you choose 0 to 10 ampere range at the start, and that's the precaution. We always use the maximum range at the start of the experiment. And then if I see that the deflection is very small, then I will decrease, then I will bring to the next lower range. Okay. So for larger amount of currents, the range will be this one. For the smaller amount of current, the range will be this one. All the current readings are such that we cannot use these two ranges. Okay, so let me check. Let me show you my answer. It's a little complicated question. You see, start with 10 ampere, 0 to 10 ampere scale. That is always what we will do. We always put the ammeter in the maximum range. Okay. Use lower scale if the reading on the ammeter is small. If your pointer moves a very small scale, then we will lower the range. 10 ampere scale used for 1 ampere to 1.8 ampere. So you see the readings of the current which are from more than 1 ampere, or 1 ampere or more than 1 ampere, we will use this range from 0 to 10 ampere range. For the lower readings of current, use the scale from 0 to 1 ampere. You see, none of the current values for our filament lamp is less than 0.2 ampere, which is 200 milliamperes. So we cannot use the two last options, this 0 to 100 milliampere or 0 to 10 milliampere. We can only use this range, 0 to 1 ampere, sorry. So this 2 number marks question is little very technical, and it's little difficult to phrase the answer. So hopefully you have understood, and you will be able to write and understand these 2 marks. You will be able to get these 2 marks. Then he says, state how the figure 9.1 shows that a lamp does not obey Ohm's law. Very easily, if the things which obey the Ohm's law, their IV graph is always a straight line. You see, the gradient remains constant. It's a straight line. But the graph which we have for our filament lamp, it's not a straight line. Its gradient is not constant. Its gradient is changing. It's a curve. So that shows that it's not obeying the Ohm's law. That shows that the voltage and the current is not directly proportional to each other. So the gradient of the IV graph for lamp is not constant. The gradient is not constant. That's why we say that it's a non-ohmic conductor. It's not obeying the Ohm's law. So that was the C part. Hopefully you understood the answer. Okay. He says, using the figure 9.1, the graph which was given to us, determine the resistance of the lamp when the voltmeter reading is 0.40. Okay. when the voltmeter reading is 0.40 volt and when the voltmeter reading is 6 volt. Okay, so we will go to the graph, and he says, what does he says? Let me, I just wrote 0.60 volt and 6 volt. Okay. Zero point 0.4, 1, 2, 3, 4. So from here you go up, you check what's the reading. So the voltage is 0.4 volt and the amount of current will be 0.5 ampere. You know the R is equals to V by I. So 0.4 divided by 0.5. So this is how you will find the resistance. Then he says 6 volt. From 6 volt, from 6 volt is here. From here you go up and check what's the amount of current. That is 1.8 ampere. So you know R is equals to V by I. So 6 volt divided by 1.8 ampere, and that will give you the resistance. So this is how I will use the figure 9.1 for the given voltage. From the figure 9.1, I will find the amount of current at that voltage for the filament lamp. And then I will use the formula R is equals to V by I, and we will be able to find out the resistance. So this is how you use, that's the D part for both these parts. There's a 3 marks numerical. And let me show you, I have done this on a paper. Okay. So you know V is equals to IR, I will be equals to V by R will be equals to V by I. This is the resistance. The resistance will be V by I. So from the figure, I know when the voltage is 0.40, the current is 0.5. So 0.40 divided by 0.5, that gives you 0.8 ohm. So the resistance of the filament that will be 0.8 ohm. Then in the second part, you know, he says 6 volt, and from the figure 9.1, I checked how much current will be flowing at 6 volt. That was 1.8 ampere from the figure I know. So R is equal to V by I, that will be 6 divided by 1.8, and that will be 3.3 ohm. So the resistance will be 3.3 ohm. It's a 3 mark numerical, and I hope that you have understood this numerical. Okay. Okay, so next question is the E part. He says, explain why the resistance of the lamp changes as the voltage changes. You see, as the voltage increases, more current starts flowing through the lamp. You see, the power consumed by the lamp increases, and that's due to that, the heat produced in the filament also increases. And the temperature of the filament increases. When the temperature of the filament increases, its resistance also increases. Okay, so at higher voltages, when you're changing voltage, you are making the voltage higher and higher for the filament lamp, and that increases the amount of current flowing through the, and the power, you know, power used is IV. Power is used to IV. The more power the lamp is using, the more hot it will become. Its temperature will rise. So when the temperature will rise, its resistance will also rise. So let me show you my answer. As the voltage increases, the temperature of the filament increases. This increases the resistance. Due to the rise in the temperature, you know, when the temperature will rise, obviously the resistance will also rise. Okay, the next question is, state how the resistance of a wire depends upon its length and how it depends on its cross-sectional area. You see, the length and the resistance, they are directly proportional to each other. The length and the resistance, a 2 mark question. He says the resistance is directly proportional to the length. and the resistance of a wire is inversely proportional to the cross-sectional area. It's a 2-mark question, a very famous concept, and here I can show you. Resistance is directly proportional to the length of the wire, and the resistance is inversely proportional to the cross-sectional area of the wire. It's a straightforward question. Okay, the last part is coming up. The student obtains a long sample of the same type of wire as the filament in the lab. The wire he obtains has the same cross-sectional area as the filament. He cuts a 1 meter length of the wire and measures its resistance at room temperature. He obtains the value 16 ohm. Using the appropriate resistance value from the D, estimate the length of the filament wire in the lab. It's a very simple question on the length and the resistance, and they are directly proportional to each other. So I will use the method of proportionality. Let me show you. The method of proportionality you have learned in your mathematics. Okay. So length and the resistance, when the length is 1 meter, the resistance is 16 ohm. And the first resistance we calculated was 0.8 ohm. So 0.8 ohm. So what will be the length? So both of them, because they are directly proportional, so I will write 1 by x is equals to 16 by 0.8. So then cross multiply. So you will have 16x equals to 0.8. 16 go on the other side, it will divide. So you will have x equals to 0.8 divided by 16. X will be equals to, on your calculator, when you put these values, it will be 0.05 meter. So when the resistance of the that wire was 0.8 ohm, its length will be 0.05 meter, which will be like 5 centimeter. So that is the last part of the question number 9. It was a 2-mark question, and that question is brand new question, and its wording is little tricky. Okay, so let's have a look at the marking scheme. So the question number 9 is showing up on your screen. Its marking scheme is showing up. What you can do, you can pause the video and take your time with this marking scheme. This is the rest of the portion of the marking scheme for the question number 9. And you can pause the video and you can take your time with this marking scheme. Okay. So let's move to the question number 10. Table 10.1 contains details of the nature and some properties of alpha, beta, and gamma emissions. So here we have alpha, beta, and gamma, their nature, their charge, and penetrating power. Okay, so first of all, we have the alpha. It has 2 protons and 2 neutrons. Charge on them is positive. Charge on them is positive. Penetrating power is very low, just few centimeters in the air, 3 or 4 centimeters in the air. Its penetrating power is very low. It will be stopped by a paper. Beta particles, it is like electron. You write here electron, its charge is negative. It is stopped by the 5 millimeter of aluminum foil. Gamma, the gamma, their nature is electromagnetic. They are electromagnetic in nature, and they're like electromagnetic waves. The charge on them, they are neutral. They don't have any kind of charge. Their penetrating power, they can only be stopped by a few centimeter thick lead sheet. Otherwise, they cannot be stopped. So this is how you will fill this table. It's a 6-mark question. Okay? Complete the table 10.1 by filling in the missing details. It's a 6-mark question, for God's sake. Okay, so very carefully fill this. It has huge number of marks. Okay, so we're done with this question. The question number 9 is showing up on your screen. And you can see this is how you will fill it. So alpha is positive. It has positive 2 charge stopped by the paper. Beta is electrons, and gamma, they're electromagnetic. They don't have charge. They are stopped by a few centimeters of lead. It's a 6-mark question. They carry huge marks. Okay. Now, surgical instruments in sealed plastic bags are placed in thin plastic boxes. So those instruments are inside the plastic bag. Then we have a plastic box. A conveyor belt takes the boxes close to a cobalt-60 source, which sterilize the instruments. So here we have cobalt-60 source, and it is giving out radiation, and that radiation, when passes through these boxes and touch the surgical instruments, they are sterilized. The germs are killed. So they are moving on this conveyor belt, and here is that radioactive source. So around it, we have thick concrete walls so that the radiation cannot go out. Okay. He says the cobalt-60 source is radioactive isotope of cobalt that emits gamma radiation. So the gamma radiation is given out, okay? Remember that. Describe what is meant by the term isotope. Isotope means the atoms of the same element which have the same proton number but different neutron numbers. So their proton number will be same, but their mass number will be different. So they are isotope of each other. They have the same proton number, but their number of neutrons in them are different. So their nucleon number, sorry, I said their nucleon number will be different. So it means that they will have the same proton number, but their mass number will be different from each other. So that is the definition of the isotope. So let's check the second one, then we'll see how my answer. Suggest a property of gamma radiation that enables it to sterilize the instruments in the bags, in the boxes. Gamma radiation has very high penetrating power. Plus, the gamma radiation carries a lot of energy. It has a lot of, because its frequency is very, very large, very high. So it has energy in it. So due to that, it can kill germs. Atoms which have same proton numbers but different neutron numbers. They are isotope of each other. Gamma can penetrate through boxes and it has high energy. It has high frequency, it has high energy. Gamma can penetrate through boxes and it has high energy because it has high frequency. Now, the next question coming up on your screen is, state why a source emitting only alpha radiation cannot be used in this way. You see, if you use a source which is emitting only alpha particles, because the penetration power of the alpha particles is very low. So they can only penetrate 2 to 3 centimeters of air. So if the alpha particles only are given out, they will not be able to travel through air and reach the boxes. Plus, they will not be able to penetrate through the plastic boxes and through the plastic bags and reach the surgical instruments and sterilize them. So the alpha particles cannot be used because their penetrating power is very low. So they cannot penetrate through the air and the plastic boxes and the plastic bag and reach the surgical instrument. So that's why we don't use them. Alpha radiation has very low penetrating power. That's why we are not using them. They will not be able to penetrate through the plastic bags and plastic boxes. The next part is the half-life of cobalt-60 is 5.3 years. Explain why a source with half-life of 5.3 minutes is unsuitable for use in this application. You see, if I use an isotope whose half-life is only 5.3 minutes, or a source whose half-life is only 5.3 minutes, so that source will very quickly will be disintegrated because its half-life is just 5.3 minutes. So very often you have to buy a new one and put it there. So you have to frequently buy the new source, that radioactive source. You have to purchase it new very often. So that's why we use that cobalt-60, whose half-life is 5.3 years. So once you put it, it will work for a long time. You don't have to buy it again and again. So source will be needed to replace with new one very often. That's the reason we are not using it. Okay. So let's check. Okay, so let's move to the next one. These are the questions which we just attempted. Okay, so here we go. He says the Geiger and Martin performed an experiment in which alpha particles were fired at a thin film of gold. Figure 10.2 shows an alpha particle passing close to the molecules of the gold atom. So here we have the nucleus of the gold atom, and when the alpha particle came here, it reflected away from it. Explain why the alpha particle is deflected. You know the alpha particle has positive 2 charge, and the nucleus also have a positive charge. So because they both have the same charge on them, they both are positively charged, I mean, so they will repel each other. That's why the alpha particle has been deflected, because the like charges repel each other. We show you my answer. Alpha particle has positive charge and is repelled by positively charged nucleus. Because they have the same charge, so they have repulsion with each other. Okay, the next question is, let's go from there. That was a 2-mark question. In the experiment, most of the alpha particles pass straight through the foil without deflection. Explain using ideas about the structure of the atom why this happened. You see, most of the alpha particles, which they took gold foil, a very thin gold foil, and they bombarded it with the alpha particles. And you see, they took a gold foil, a very thin gold foil, and they bombarded it with the alpha particles. And most of the alpha particles went straight, like nothing came in their path. So they went straight. So that the reason is that the most of the atom is an empty space. There is nothing in the atom. The most of the space in an atom is empty space. There is a very small nucleus in the center, which has positive charge and which has mass. So most of the alpha particles went straight through that empty space, and some who came in near the nucleus of the atom, they were deflected. Rest of that alpha particles went straight, because most of the atom is empty space. There is a very small nucleus in the center, and which has positive charge. So let me show you my answer. Most of atom is directly is empty space. Nucleus is very small as compared to the atom. So the nucleus in the atom is very small. So that's why the most alpha particles went straight. So my dear students, we are done with the question number, I think, question number 10. And by doing this, we have reached the end of the paper. So let me show you the marking scheme for the question number 10. Okay, so here we go. So the marking scheme for the question number 10 is showing up on your screen. What you can do, you can you can pause the video and you can take your time with this marking scheme. Okay, so here we go. You can pause the video and you can read this marking scheme. It is very, very important to always check the this. You see, for example, I wrote there most of an atom is empty space. Nucleus is only a small part of atom. So alpha particles rarely pass close to the nucleus. Okay, so that's why the most of the alpha particles went straight. Okay, so add this sentence in your answer. So that's it. Today we have done. Okay, my dear students. Okay. So by the question number 10, we have reached the end of this paper. In this video, we have solved May, June 2021, Physics 505421, Section B. We have done the question number 8, 9, and 10 of this paper. So this paper is completed. Now, if you find this video helpful, kindly subscribe to my channel and like this video. If you find it helpful, don't forget to share the link of this video on your Facebook and on your Instagram, because that will be a great appreciation for my work, and that is a fuel for me. Okay, so thank you very much, everybody. I hope that this video will help you in preparing your exam. So thank you very much, everybody. Have a good day and God bless you all.